Hello everyone, my name is Apple James and my colleague is Mwanguzimasi, and we are here to present our project by the type of contrastive attention-based knowledge distillation for coffee yield estimation using capsule networks. And below are our key terms which we shall find within our project. Well, our table of content is not far different from the rest of the people, which we begin with introduction and end with the acknowledgement. Talking of coffee, coffee is one of the Uganda's largely exported crop of which the table, the graph that we are seeing on the screen, was actually extracted from the Uganda Coffee Development Authority. And it shows the coffee that was exported from October 2023 to September 2024. And then the red line shows the value in US dollars. Well, in this case, coffee yield was estimated using the traditional method, which was extrapolation, and it was lacking a bit of standardization, and that is why we came up with our project to solve that. Well, when we first talk of our related work here, we are talking of some people, there are some people actually who talked about of implementing machine learning in agriculture research, which include the Subhadra Mishra, uh, Dibahoti Mishra, and Goa Hari. And well, some of the machine learning algorithms, or let us talk models that they talked about, include the attention mechanism and capsule, of which we are going to use it here to estimate the, of course, to focus on the important image features, reducing noise and improving accuracy. The capsule neural network, which was introduced by Sabua et al., improved the feature representation and present partial relationships between objects, making them ideal for small object detection like coffee cherries. And then there was contrastive learning. In this case, it was just supposed to differentiate in terms of classes. We put them in classes of ripe, unripe, and ripening. Knowledge distillation, we're just going to train a model, a teacher model. We can be a capsule, and then the student model probably can be the attention mechanism, and then we transfer from the capsule to attention, and it is going to be fast and lightweighted predictions to make fast and lightweighted predictions. Well, our problem statement in this case was to solve the manual yield estimation with lack standardization, leading to inconsistent yield predictions and poor resource allocations. And why this matters is that farmers and policymakers struggle to make data-driven decisions due to unreliable forecasts, inefficient resource allocations, impacts profitability and sustainability in coffee production. So there was computational problems. Well, training these models, deep learning models actually require a high computational power. And then also, when we talk of the farmers, farmers, smallholder farmers lack access to high performing computational infrastructure. And then when we also talk of the real-time processing limitations, deploying models for real-time yield estimation demands optimized performance without sacrificing accuracy. When we talk of the research questions and objectives, well, the objectives for this case, we are going to demonstrate, it was to demonstrate the potential of the contrastive attention-based knowledge distillation and capsule networks for accurate coffee yield predictions. And the next one was also to model how this framework addresses the challenges of the traditional yield prediction methods like extrapolation. And the next one is to outline how this improves the coffee yield by the features of the coffee trees. Another one was to also propose the methods in improving efficiency of yield prediction methods for coffee farmers, that is industry, stakeholders, and researchers. And some of the question is, can contrastive attention knowledge distillation improve the accuracy of coffee yield prediction? Then how does the performance of the capsule neural compares to traditional that CNN, and uh, what what role does contrastive learning play in feature extraction for yield estimation? And how can knowledge distillation optimize development without sacrificing? Well, we also got to realize that there were some contributions that our research made, which was improve accuracy of coffee yield predictions using novel machine learning techniques, automation of the yield estimation process, reducing labor and time, requirements, then framework for optimizing resource allocation and harvest planning. And the next one was also contributing to sustainable coffee production in Uganda. Well, when we talk of our methodology, we actually had to analyze our data. And in this case, the image quality, we had to get the high resolution of image qualities, and the argumentation we had to cause crop it. It involves cropping and other stuffs, that argumentation. And then the feature extraction, which was to focus on the coffee cherries, leaves, and maybe canopy. And then modeling training, which was a self-supervised learning using the contrastive learning in this case. And distillation and other models that we actually use, both the deep learning and the traditional methods. And the final prediction for estimating yield. Well, when we go to the dataset description, we are using the RoboFlow. We use the RoboFlow to label our datasets. We classify them into 4 classes, which is the unripe, ripening, and ripe, then the coffee tree. In this case, the annotation instances show us all whereby we annotated all these things. And then our image specification is we just need the size from 1 MB to 10 MBs, and then the dimensions as provided below. So when we talk of these graphs, explaining a bit of these graphs, we are going to pass through the histography of cherry counts by ripeness. And well, this one is, it helps us visualize how coffee cherries are distributed at different ripeness levels, which can be used to estimate the yield readiness. And then histography of leaf count. Well, this one is the next one. Well, this helps us understand how leaf counts varies across samples, and then a normal or a skew distribution may indicate patterns in plant health or growth stages. When we talk of pair plot for key features as the next graph in our next slide, sorry, the network is disturbing a bit, but the next slide is loading. Yes, okay.
Hello.
Sorry for disturbing there. Well, our pie chart is supposed to help us categorize plant coverage and understand whether majority of plants have significant leaf coverage for optimal growth. And then the pair plot for key features is actually useful for detecting trends and potential dependencies among the key variables. Thank you. Let me invite my next colleague to pass us through.
Hello, my name is Masi Mwanguzi, and I'll be taking you through the rest of our presentation. So here we have 3 graphs. We have the box plot, the scatter graph, and the histogram. The box plot essentially is showing how data is dispersed. So the longer the box, that means the more the data is dispersed. And we are seeing that in this box plot, in the 3rd range, that is where we have the highest median. And moving on to our scatter graph, which is the coffee cherry versus the leaf count, the different dots in the different color representing the different cherries. And with this, we see that there is a positive correlation. So it's implying that the more the number of the leaf count, that means the more the cherry count. And from that, we shall be able to determine the yield. And then moving to the histogram, which is showing the canopy, the green pixel coverage. So if the green pixel coverage is high, that means there is a dense canopy within that data set or within the images. Then moving on to the next one, we have a bar chart, which is showing the different cherries we have within the data set, showing that we have more green cherries, followed by the yellow cherries. Then the red cherries are very minority. And then we have our heat map, which is showing how the different cherries, the red, yellow, and green cherries correlate with the other. And there is the intensity scale, the higher the correlation, the darker the colors. Yes. And then moving on to the next one, we have our scatter graph showing the canopy coverage versus the leaf count. So if you have more leaves, that means there is canopy, like the canopy is big. Yes. And then for the violin plot representation, when the violin is wide, that implies that the data is scattered. And when the violin is narrow, that means that the data is kind of together. So here we are seeing that from the range of 1,000 to around 2,000, that data is so scattered. Yes, and then for our density plot, it's showing the canopy coverage in percentage. It's the same analogy as for that of the violin. So the narrower, that means the data is more organized, and the wider the density plot, that means the data is scattered. Then these are some of the graphs we got from running some of our models. The CNN model results, the attention-based and the naive model. And these are model accuracy graphs and model loss graphs. As you can see, they are varying from one model to another. Then moving on to our next, we got confusion matrices, and the leftmost and the rightmost were got from the support vector having the stochastic gradient descent, which is for hyperparameter tuning. And the y-axis represents the true label, which is supposed to be the actual yield, and the predicted label is the one that is predicted by the model. So for example, the confusion matrix of the test set, we are seeing 190 samples in the first square. And that means that 190 samples were predicted by the model as low yield, which is actually true. But when we come on the 159, it's showing that 159 samples were predicted as high yield, yet they are low yield. So the same analogy applies to all the other graphs. Then we have some tables. We have our UIs and our principal component analysis. The first image is for the interface for a farmer to input their image. And once they input their image, we are seeing the results screen where they're able to tell how many ripe cherries, overripe, semi-ripe, and unripe they have. And then they're able to detect how much they're going to obtain from that tree. And the principal component is essentially separating the different coffee cherries in the different trees. Then moving on to, we have some tables that we obtained from running our models. We have the CNN model evaluation matrix, and we're seeing the accuracy was 90%. And then we have the regression model result where we use 50 epochs, and it was able to predict on the terminal that we have 5.13, but it wasn't working well with the UI. So we decided to use the YOLO 8, which is having the black box representation. And with it, we're able to get proper yield estimations. Then the challenges we anticipate is the complexity of the models and the different ways these models have to work together to give us the right predictions. There is also a problem of data imbalance. In case the different classes have different amounts, there's going to be bias. So, and then the environmental variations when the farmers are taking pictures. So if there is too much sunshine, it might affect the picture. So it might not be able to make the right predictions. But how we plan to kind of counteract these challenges, we plan to use the adaptive routing for the capsule network, and then data augmentation to kind of reduce the imbalance, then to incorporate a multimodal model to deal with the environmental sensor data. So the capsule network and the contrastive learning provide a robust way of preserving spatial hierarchies when carrying out feature extraction. And we believe that our study is going to increase on the precision mechanism of yield prediction, and it will reduce on the labor. What we plan to do, we plan to incorporate IoT sensors so that we can do real-time analysis, and we plan to expand our work to other crops like maize, rice, and cassava. And then we plan to make this work an application on the phone so that it's easier for the farmers to use. Yeah, we would like to thank Makerere University for helping us get knowledge about machine learning, Manly platform, and RoboFlow, where we're able to get our data sets. And the National Coffee Research Institute and the Uganda Coffee Development Authority, where we're able to get some insights about the coffee of Uganda and how it works out. And would also thank Ateka and Basen, whose work we based on to build on our research. Yes.